To get a better understanding of electric potential energy, and its parallels in gravity, we're going to look at the two side by side. So we're going to look at gravitation and electrostatics. Now, we all know that the Earth is flat. Well, of course, we all know that we can approximate the Earth is flat. If we're talking about immediate surroundings, so the Earth, of course, has a gravitational field that's radial. But if we're looking at a small section on the surface, G may as well be uniform all around us. Let's say we're playing soccer. We have a soccer ball, and we want to kick the ball up into the air. When the ball gets to a certain height, we know that it has some potential energy associated with that. Quantity mg times h. The mass times the gravitational field, 9.8 meters per second squared, times its height in meters. Will give us a value in joules. That value in joules can be realized into kinetic energy. We allow gravity to do work and return the ball back down to the surface of the earth. So potential energy is the capacity to do work. Now if we compare an analogy in electrostatics, if we get a line of charge or a sheet of charge, let's say positives and negatives, spaced apart, they'll get a uniform electric field set up in between the two. Now if we put a charge, the equivalent of mass, a charge in that uniform electric field, there is some force associated with that, as we know already. Now if we choose a distance, 0, just like we had to choose a height, 0, we can associate that charge and that distance with some energy. In fact, it's almost the same equation, U equals Q ED, just like mgh, it's a quantity, a field, and a distance. Now that can be realized into work. If you let that charge go, the charge will move, depending on if it's positive or negative. It will go right or left. So that work, that potential energy in joules will be converted to motion energy, and that is, work will happen. So that is the case with uniform fields. That's great and that's convenient. But what if we have a situation where fields are not uniform? So take the case of two masses, M1 and M2. M1 sets up its own gravitational field that interacts with the field of mass 2. If they are separated by distance r, h no longer seems quite relevant. We're not talking about straight up. We're not in a uniform field anymore. We use separation distance r. But M2 should still have a quantity, a potential energy mgh or mgr. Now that little g is not 9.8 meters per second squared anymore. Of course, it has to be calculated, big G times m1 over r squared. So substituting, we get a quantity for gravitational potential energy of any two objects, M1 and M2, separated by r number of meters in our universe. So that is a quantity in joules. If you let these two masses move, then, depending on their initial conditions, that energy could get converted into motion energy, or work could be done. It is the same for charges. The difference is, of course, we can have positive and negative charges. But let's say we have a positive charge Q1, negative charge Q2, separated by distance r. We follow the same process to get a very similar looking potential energy equation. So it's the energy in joules associated with two charges, Q1, Q2, r number of meters apart, with Coulomb's constant scaling the interaction, determining the quantity of joules. So those charges, when released, would move depending on their relative signs, and that would be work happening then. Okay, so what is potential then? That was potential energy. That's useful. But there's something called electric potential that's quite useful as well. Now if we take the case of uniform fields, whether they be gravitational with a mass in them or electric with a charge in it, we have very similar equations to calculate those quantities in joules. But what if we want some different information? What if we want to know energy per unit mass or energy per unit charge associated with that field? Like if I drop a mass in a gravitational field, how much energy will actually be associated with that mass, independent of how much it is? So if I drop a bigger mass, there should be more energy, smaller mass, less energy. I just want to know how the field scales according to that idea. So if you divide the field by the mass, you get that quantity, Gm1 over r. You do the same thing for the potential energy. If you want to know if if you put a charge Q2 in a electric field, you want to know the joules per coulomb. Like how many joules of potential energy will that charge have per unit charge? So no matter how big or small the charge quantity is, I just want to know how much energy is associated per unit charge. We get that KQ1 over R. So we call that potential. Not potential energy, but that is electric potential. It's given uppercase variable V. It comes in joules per coulomb. So it again is energy per unit charge. So if we put those two ends of that evolution of that equation together, we get a fairly useful equation showing the relationship. That potential energy is the energy per unit charge times the charge in the field. Now, let's imagine a case where we have two different potentials. So we have some potential V and then some potential of 0V, and we have a charge, Q, that's in this area. We want to move that Q from one potential to another. So there's 0 joules per unit charge associated with V equals 0, and then V has some value of an actual joule per unit charge. If we move that Q a distance R, there is energy required to make this happen. In fact, it's exactly equal to Q times V. But what is V? I mean, we might know that V in joules per coulomb, but if we plug in what we know for V, which is KQ over R, a different Q, the Q that's responsible for making that potential, is that the charge is up top, up bottom, is it multiple charges, is it a line of charge? Well, if we already know V, just like if we already knew a uniform field, then we wouldn't have to worry so much about that. But if we're talking about two charges, Q1 and Q2, each charge has its own potential field. They also interact equally and oppositely with Coulomb's law, exert a force on each other. So if you look at those two equations together, so if we're looking at the potential from Q1 and the force between the two, we'll compare them. If we want to make V out of force, we can see we need to cancel out the other charge. So F divided by Q2 and then multiplied by a distance. So you can imagine a distance equal to R. That would get us to potential. So this is getting us actually closer to relating potential to electric field. So you can see that F over Q, that is electric field. So we just discovered the relationship between electric potential and electric field, and that is the potential is the field times distance. Now, there's a big warning here. In all of this, we've ignored sign conventions, which will become important when we're talking about charges, because unlike mass, which doesn't seem to have a positive and negative, a charge does.